Hello, today we're going to be looking at a integral and possibly its derivative given a table of values. We're going to be looking at estimating integration and function values using just a table. So for this question, which I'm calling the leaky truck problem, a large commercial truck has an engine oil leak. Now these big trucks you see on the highway, they hold a lot more oil in their engine than we do in our cars. The rate at which the oil is leaking from the engine is modeled by a twice differentiable function L, where L of t is measured in liters per hour and t is in hours for 0 less than or equal to t less than or equal to 2. The table shows the values of L for selected values of t. One of the things that when you read a question like this that you want to make sure that you're aware of is this word right here, because this could end up being really important, especially to finding the amount of oil at any one time or interpreting your answer. So we want to underline that, that word leaking. Okay, let's take a look at the first question that's going to go with this. All right, let me just paste that right there, and here we go, we'll put it there. All right, first question. Approximate the value of L prime of 1. Explain the meaning of your answer using proper units. Okay, so L is liters per hour, which we would think of as a rate of change. But L prime then is the rate of change of this, get back to my brush, of this per that. So the units is liters per hour per hour. And I'm going to go ahead and write that right now, because a lot of times students tend to leave that off. And on a question like this, if it's a 1-point question on an AP exam, you're not going to get any points without the proper units. If it's a 2-point question, without doing any calculus at all, just knowing that L prime means L per, the Y per X, that gets you half the points right there. And that's huge. So this is liters per hour per hour. And you can just write it out or put it like that, or liters per hour squared. Anything like that's going to be acceptable. All right, let's go ahead and see if we can estimate L prime of 1. A lot of times they'll ask you to estimate L prime or a function value given a table, but they won't give you a number here that appears anywhere in your table. If they do that, you need to use 2 values from the table that surround it. If they give you a value like they did here of the table, well, then we just need to make sure we use that number. We can either use 1 to 3/2 or 1 to 1/2. Using 1 to 2 or 1 to 0, that wouldn't be a mistake, because that wouldn't give us as good an estimate, and then they would not accept that answer. So L prime of 1, and I'll use the approximate symbol because that's just good habit. It's not something that they count off for not using, but it's good habit, because we're not saying this is exactly, we're estimating it. Okay, well, L prime of 1 is going to be approximately the rate of change, the slope of the secant line, from L of, let's do L of 1. I'm going to do it from 1/2 to 1, actually. So L of 1 minus L of 1/2, okay? That's f of b minus f of a, right? Our difference quotient over 1 minus 1/2. Okay, so that's going to end up being L of 1 is 5, L of 1/2 is 3, and I'm going to move that on 1 minus 1/2. I'll just leave it like that. And that's going to be liters per hour squared. All right, so there's no reason for me to go and try and evaluate this quotient here. Especially, the top is 2, the bottom's 1/2, means the answer is going to be 4, but that's really not necessary for us to do that. And we don't want to make any mistakes, and it doesn't give us any extra points for doing it. So let's explain the meaning. that this is the rate of change in the amount of liters of oil that leaks per hour. So this is, or you might think of it as the acceleration of the leaking. And we're just looking for anything like that. We'll just say rate of change of the rate of leak. Per hour. Okay, and that's going to get us, a little sloppy there. That's going to get us full credit. That's fine. Okay, so that's done. I'm just going to go ahead and I'm just going to take that off so I have room to work. All right, just pause the video if you need to write it down. Okay, let's go get our next question now. All right, 1 second while I bring that up, please. Here we are. Okay. Next question. At least how many times must the rate of leakage be 3.5 liters per hour? Okay, so that is a value for L. Okay, so this here, liters per hour, that perfectly matches this. They're asking how many times must L, a value here, be 3.5. Obviously, it never occurs on our table. It could occur on our table, but it wouldn't necessarily tell us the answer there. What we need to be using is a theorem that tells us when f equals a value. Not when f prime equals a value, not when the integral of f equals a value, but when f, or in this case, L equals a value. That's when I want you thinking intermediate value theorem. Okay? So in order to explain and justify this, we need to be able to say that this function is continuous. That is absolutely necessary to say. It's not right if you don't say it. You have to show that you're using the theorem. And we wouldn't want to apply it if it wasn't true, because you can't make that kind of conclusion. So is L continuous? Well, it is. And we're going to say why. To get full credit, we're going to say why it's continuous. And I'll just kind of abbreviate that, continuous, right there. And we are going to say that it is continuous because L is differentiable. Okay? That's all we need to say. Being differentiable requires the function to be both continuous and have a local linearity, otherwise called smooth, right? So because continuity is a requirement for differentiability, we know it's differentiable, we know it's continuous. All right, I'm going to just go ahead and establish some places where L is less than or greater than 3.5 and see how many times we can do that. Well, we got L of 0, that's more than 3.5, right? But then after that we have, and it could be any time in the table, but it looks like it's just the very next time, right? L of 1/2. Okay, that's one place. Is there another place that we could make the same kind of sandwich here? Sure can. Let's keep going with the L of 1/2. Well, that's less than 3.5, which is less than L of 1. And we can do it again. We can say L of, let's see here, 3/2. Well, L of 3/2 is greater than 3.5, which is greater than L of 2. So I was able to establish 1, 2, 3 places. So by the IVT, we're going to have to say that, okay? We established continuity, we established the in-betweenness that's required, and now we have to cite the intermediate value theorem. If you don't cite it, you don't get credit. By the IVT, L of T is equal to 3.5 at least 3 times. We don't know, it could be more, but we know it happened at least 3 times. So I'll say at least 3 values of T. Okay, and that's it for that one. And once again, if you need to look at that longer, go ahead and pause, but I'm going to go ahead and just clear out this question so we can make room for the next one. And let me go grab that next question right quick. All right, it says using a Wright-Riemann sum of 4 intervals to estimate, I should say use a Wright-Riemann sum of 4 intervals to estimate 0 to 2 of L of T dt. Explain the meaning of your answer. Be very, very careful with these. Make sure that this is asking you to integrate L before you start doing a bunch of adding and stuff. Well, a good hint is they said, to use a Riemann sum. That's a pretty good indication. All right, so we're going to show the values that give us this answer. So we're going to say from 0 to 2 for intervals. So we'll go 1, 2, 3, and 4 using the right values. So I'm going to do L of 1/2, which is 3, plus L of 1, which is 5, plus L of 3/2, which is 5, plus L of 2, which is 3. It probably would be best to go ahead and say that you're doing L of 1/2, L of 1, L of 3/2, L of 2, but you can't leave it like that. You got to take it to here. And then there's no reason to add that. Yeah, we should be able to add that without making a mistake, but it's not worth it. It's a waste of time. We are going to make sure we put units on our answer, though. We are integrating liters per hour, so we're just going to remove a per. So this is liters. We're going to explain the meaning of our answer. So this many liters leaks out over the course of 2 hours. Leaks out, and we'll give the interpretation for T from 0 less than or equal to T less than or equal to 2. And that's it for that one. All right, let's take a look at the next question. Just one more second while I pull it up. All right, this is just kind of a follow-up question. Actually, probably should have left what I had up there, but this is related. It says, if the truck started with 40 liters of oil at T equals 0, estimate how much oil was in the engine after 2 hours. Well, we just estimated the total amount of leakage to be 16 liters, was how many liters of oil fell out, right? So if we started with 40, we would just basically copy down what we had on the problem before, which was 3. Now we'll put that in parentheses, make sure we do it first, right? 3 plus 5 plus 5 plus 3, because that's our Wright-Riemann sum approximation for the total amount that leaked. And so 40 minus that amount, because it's leaking, it's decreasing, that's going to give our answer for how many liters are currently still in the engine. Okay? So we obviously got a big problem. Hopefully this isn't something that happens in the real world. That's a lot of oil going into the environment. But in the math world, anything's possible, right? Okay, so that pretty much is done. That's it for that one. All right, just a few more to go. I know you're probably getting bored with this oil problem here, but bear with me. We got just 3 more to go. But this is a good, rich problem that we can get a lot of practice from. So I want to make sure we use it to its fullest. All right, we're going to use the table to evaluate the integral from 1 to 2 of L prime of dt. Explain the meaning of your answer using proper units. Okay, this is a kind of a gotcha kind of question here that a lot of people miss, but it's super easy. Let's take a look at some of the hints. Notice that word there. That word does not say estimate. It says evaluate. So for some reason, you're supposed to be able to get the exact value of this integral given a table. Okay, so that's to make you think I'm not using a Riemann sum. Notice they also didn't say to use a trapezoid, left, right, or anything like that, because you shouldn't need to. Notice that the integral is not of L, but of L prime. Well, the fundamental theorem of calculus tells us that the integral from 1 to 2 of L prime of t is equal to L of 2 minus L of 1. That's what that equals. Well, we know L of 2. We know L of 2, that's 3. Right here from the table. We know L of 1, that's 5. So the answer is -2. Now, what's the units? Well, if you integrate from L prime up to L, well, then the units is the units on L. So it's liters per hour. So, but what does it mean? And I'm not going to write this down, but I'll just say it. What it means is that the rate of change in the liters per hour, the rate of change is -2. The amount of oil that is leaking per hour will change by 2 from hour 1 to hour 2. It's just simply the change in the Y value. All right, let's take a look at our next question. 2 more. Get rid of that one. And bear with me again while I pull up the next one. All right, is there a time when the rate of change of L must have been 0 liters per hour? Explain. Okay, so it's asking about a rate of change of a rate of change. We know L is a rate of change, but so when we're asking for a rate of change of the function we've been given, that's not IVT, that's MVT. That's mean value theorem. Or in this case, since it's equaling 0, we could even use the more specific Rolle's theorem, excuse me. So I'm looking for a time when the secant line of L has a slope of 0. Well, a slope of 0 simply means that the y coordinates are the same. And I think you can see that right here. Can you see that? Can you see that the change in the L value from 1 to 3/2 is 5? So we can say, we're going to say the condition set. L is continuous and differentiable. Need to be on an open interval. If I want to, just saying that should be enough on this situation, but we'll go ahead and say, on the interval that we're talking about. All right, it is continuous and differentiable. I will go ahead and use Rolle's theorem on this one. L of 1 is equal to L of 3/2. So because it's continuous and differentiable, and I've got L of one t value is equal to L of the other t value, that means that the rate of change between those two values is 0, so I could use the mean value theorem here, or I can use Rolle's theorem because they're equal. So I'll just go ahead and cite. Either one works, but I think it's a little less writing here to say by Rolle's theorem, there is a time when L of t equals 0. Excuse me, L prime, the derivative, that L prime of t equals 0, from 1 less than little trouble writing today. L but less than t, less than 3/2. So we know that must have happened. At some point, the rate of change was 0. The secant line was flat. Okay, so we'll go ahead and move on to one last question. All right, the sum sigma from k equals 1 to n of L of 1 plus k over 2n times 1 over 2n is a Riemann sum of n subintervals. As n goes to infinity, this sum is a definite interval. Express this sum as a definite interval. All right, well, they're asking us to take the limit of the sum. We should recognize that as the formal definition of the definite integral. We know that when you do a Riemann sum, if the width of those rectangles goes to 0, then the number of them would go to infinity, and that becomes a perfect area under the curve. This question, the way I like to handle it, I do not like it when it's written like that. I want to change this. I don't like having it in this sigma form. So I'm going to change it by expanding it out. Well, leave just a little bit of space here. We're going to come back and add something there. All right, so we're going to be doing a sum. So I'm going to be doing L of, well, we're going to start with k equals 1. Well, I need k equals 1. I get 1 plus 1 over 2n. Okay, need that. That's the first one. Okay, and that's really I only need that one and the last one. But I'll do another one just for, showing the pattern here. Okay, so on the next one, it's going to be 1 plus, okay, now k was 1 when we start. Remember, we start with k equals 1 and it goes up. Now k is going to become a 2, so I'm going to have to make this 2 over 2n. Okay, that's fine. All right, and then plus L. Actually, I think that's enough right there. Actually, let me erase that and just add some dot dot dot. Okay, so it's elliptical notation, and that's what I wanted to show. I think that's easier to visualize than the sigma. So this is going to keep going. We're going to do, L of 1 plus 3 over 2n, L of 1 plus 4 over 2n, all that. So eventually, though, this is going to come down at some point to the end of this sum. Well, the end of this sum is when k is equal to that number right there, n. So the last thing we're going to be adding is 1 plus n over 2n, right? That's going to be the last one that we add. Now we're going to handle this. Wait a minute, but n's going to infinity, and that's where we start getting, mind boggled. We were saying, whoa, how can I ever finish this sum if n's going to infinity? Well, let's not worry about that yet. Let's just take it quite literally what it's saying, okay? And I'm going to say, all right, well, here's my sum, okay, that this is saying, and now I'm going to take the limit as n goes to infinity. And sometimes I'll actually write it out here. When they say as n goes to infinity, they could write it out in front of the sigma, then it looks just like what would be on your formula chart. We're going to take the limit as n goes to infinity. Okay. Well, what we're going to do is just do exactly that. Let's take the limit of the first term. So if I let n go to infinity, I get 1 plus 1 over infinity. Well, we know that 1 over an infinitely large number is basically 0. So basically this term here, let's write it down here, this term here is L of 1 plus 0, okay? All right, and then, we're going to do some other stuff, okay? We're going to add some other y values, this here, and a bunch of other stuff. And then we're going to get to this last term, okay? Let's take a look at this last one. When I plug in infinity for n, I get 1 plus infinity over 2 times infinity. We could reduce the n's, though. You can see that that's really 1 plus 1/2. So as n goes to infinity, this term here, you'll notice the degree is the same, right? When you're taking limit infinity, you look at the degrees of the polynomials. Degree is 1, so it's the ratio of these leading coefficients. Well, that's 1 over 2. So this is really L plus 1 plus 1/2. So really what we're doing is we can see that the very first value is L of 1, and the very last value is L of 1.5. So we're adding up every single possible value from 1 to 1.5 of L. Well, what is that? We know what that is. That is the integral from 1 to 1.5 of L of t dt. All right. Keep in mind there are many correct answers to this particular question. Anything of the form, you could have left it as 1. You could have done an integral from 0 to 1/2 and called it L of 1 plus t, or you could have used x instead of t. Any of those things are fine. It just has to be something that can be in that same pattern. And that's it for this question.